Hello, I'm Brian Corbridge, and today we're going to be discussing the motion of falling objects for our second lab here in Physics 2211. For starters, whenever an object is in free fall, it should theoretically have a acceleration of 9.8 meters per second squared down towards the surface of the Earth. However, this is not always the case in practice because of air resistance slash the force of drag. Those are forces that act upwards against um, gravity, or if you're going laterally, it can also act against whatever direction you're going as long as you are moving with medium to resist, which in this case is air. As we dive in deeper to discover the forces of air resistance and the logistics of free fall, we set up an experiment where I dropped a ping pong ball, an orange ping pong ball, as you can see, from a height of, I would say, about 5 feet or 1.54 meters. The mass of the ball was about a hundredth of a kilogram, so it wasn't very heavy, so it should be easy for air resistance to play a big role in this. And after putting it through Tracker and analyzing it, it took about zero point 0.6 seconds for the ball to hit the ground. We'll use this information a lot later to set up our graphs and plug in our information to my glow script code. As you can see here, this is my predicted graph for the velocity versus time graph for the ping pong ball's descent. Um, as you can see, the y-intercept, or actually the x-intercept too, it starts at the origin because zero seconds have passed and there was zero velocity, so it wasn't moving yet. And since it took about, with some rough estimates, it was about half a second it took to hit the ground, and it theoretically should be falling at with the acceleration of negative 9.8 meters per second squared. So I just, did some rough estimates, and as you can see, at half a second, in between like half a second and zero point 0.6 seconds, it's about halfway, half of 9.8 or negative 9.8. So I didn't account for air resistance or anything. I did my calculations later on, which you will see. As you can see here, this was my final velocity versus time graph and position versus time graph. I had to do some calculations to calculate the force of drag. Uh, and, I used the equation force of drag equals negative b times velocity squared times the unit vector of velocity. It's hard to type out there, so I apologize. Um, and after calculating all of that, I found that the upward force acting on the ball was about 5 thousandths of a Newton, because you have to multiply acceleration times mass, and the mass was so low, so that's why the Newtons are so low. Um, so the net force overall was about 0.93 Newtons going downwards, which you can see here with the velocity. It's accelerating downwards. The slope is getting greater, or the absolute value of the slope is, and the position as well. Um, it's a side note. If I were to have dropped this ball from a higher, from a height that's, higher up in the sky, this velocity versus time will start to even out because eventually the uh, upward force will equal the downward force. So there will be no acceleration. We call it terminal velocity. Uh, it will have a constant velocity though, so it's not like it's gonna stop moving or anything. It just won't be accelerating anymore. Lastly, here's my final code on GlowScript to, make the animation, which you can't see the animation, but you can see this. I have a little arrow for the force of air resistance, a little arrow for the force of gravity, and whatnot. The length of the arrows aren't really important, but you can see the time. I have zero point 0.6 seconds because that's how long it took. 0.005 because that's how many newtons newtons. That's the B for force of drag. Um, the starting conditions are here. I dropped it from 1.5 meters up. F net, as I said earlier, 0.093 newtons. And then here I derived these from the velocity update equation and the position update equation. So that's how I got, the ball velocity and ball position. And yeah, that's about it.